A quick note here on how graph theory works is we're going to see a lot of times that graph theory is kind of built to be understood pictographically. That is, it's meant for being represented as a diagram, so when we define things in terms of those diagrams, they usually make sense. It usually seems reasonable why we call something a path or a circuit. Where when we talk about a circuit or a cycle, we are looking at something where we take some vertex and we come back around to it. So if we have the circuit with one vertex, that's just the circuit with a loop. If we have the circuit with two vertices, that's the circuit that has one vertex edge and then another edge coming back to it. Then we get to 3 and above, we actually get more meaningful things. If you have 3, it looks like a triangle, 4 looks like a box, 5 looks like a pentagon, and so on. Where the thing about circuits by themselves, these circuit graphs without anything else attached to them, they tend to just look like basic geometric shapes up to deformation. Usually when we represent these things, we like to present them in the most logical way, but we don't need to. We could twist those things around however we want. Anyway, we have that as the general construction for a cycle or circuit, and then we can also talk about taking a cycle or circuit inside of another graph, that if we have some larger connected graph, some big set of pieces, we can look at a circuit as going from one point, one vertex, back to itself through others with edges in the graph. And then if we want to talk about a path, essentially what we're looking at is taking a circuit and kicking out one edge. We're talking about something that kind of runs like a line from point A to point B, or vertex A to vertex B, thinking in our language. So if we have a path on two vertices, it's just two vertices with one edge. 3, it will be 3 vertices, 2 edges. 4, 5, and so on. Hopefully you get the picture that when we're talking about these things, if we have n vertices, we will have n minus 1 edges. So also, if you're thinking about it in that way for our circuits, we have n vertices and n edges, exactly because we're talking about just taking one thing and getting back to it in the shortest way possible with that number of vertices. And here, for a path, we're talking about taking something and going somewhere else in terms of the shortest number of edges that we possibly can, in terms of a straight line, as it were. This is what we call a path versus a circuit. Just a bit of naming, a bit of nomenclature, a bit of just specificity there that's worth being aware of. It's worth knowing what these things are, because as we're moving forward here, we're going to talk about specific kinds of paths and circuits. In particular, when we're thinking about that idea from Königsberg, that leads to a very special kind of circuit where we're trying to describe all of the edges in a graph. We're trying to hit everything that we can. We'll see that there are special ways that that occurs, as well as ways we can talk about if we get all of the edges, but not necessarily complete a circuit. Again, those are things for later, just setting the table right now with how these run. And then the very last piece that we have here for continuing to set the table is talking about what it means for a graph to be connected, or, for that matter, disconnected.